Hi guys, thanks for tuning in. In my final video for this chapter, I'm going to talk about path independence for gradient fields. All right, so we're going to start with an example that you should be fairly familiar with by now. We have f of xy, which plots out as a surface, and you've seen this surface before. We used it for showing that the net flow of a gradient field along a closed curve is equal to 0. We're going to use this surface again to try to discover another interesting property of gradient fields. So here's our surface, here's its associated gradient field, and here's a contour plot, just showing those side by side. As you get more comfortable in this course, you'll start to be able to equate all three pictures with each other. You can look at one of the pictures and kind of imagine what the other two might look like. All right, so what I'm going to do now is I'm going to compute a path integral for the gradient field of f of xy for three different curves, C1, C2, and C3. I'm going to compute the net flow of the vector field of my gradient field along C1, and then I'll do the same thing for along C2, and then the same thing for along C3. And I'm going to kind of compare my results. Now here's my C1. I have an x1 of t, y1 of t that I parameterized, and it looks like this. Now remember that these path integrals are going to compute our net change in altitude from our starting point to our ending point on the surface. So this path integral, when I compute it, it's going to tell me my net change in altitude from my starting point to my ending point. If you think of it as going on a hike, you can say, okay, I'm starting at 500 meters above sea level, and then I'm going on this hike to this from my base camp to my ending camp, and my final altitude is 1500 meters, and so I had a net change in altitude of plus 1000 meters, plus 1 kilometer, right? Probably easier to imagine if you look at it not from the gradient field point of view, but actually looking at our mountain. So you can literally imagine that you are going on a hike and you're computing your net change in altitude from your starting point to your ending point. All right, so I'm going to compute the integral of field dot tangent, and you could run this path integral through Mathematica, and you can get 0.597. You could pretend that you gained half a kilometer of altitude, 0.597 kilometers up as you climbed this mountain. Now, I don't want to give it away too much yet, but asking Mathematica to integrate in this particular case maybe wasn't the best choice because we have a piece of information here and we're armed with the fundamental theorem of calculus, so there's probably a way I could have avoided a lot of computation here, but we'll get to that later. So our net change in altitude on our surface, 0.597 kilometers. Our change in height from starting point to ending point is up 0.597 units. Now I'm going to do the same calculation, but for a C2 that happens to have the same starting point and the same ending point as the original curve, C1. You can kind of imagine that maybe you are going on a hike and you went along the parabolic path. A pretty good path from point A to point B, from start to end. And maybe your friend is also going on a hike, but they don't really have a very good sense of direction, or their compass is broken or something, and they end up going on this crazy loop from point A to point B, from start to end. But the good news is, though, they started with you, and luckily they ended with you as well. And so when you compute your path integral here, what you should expect is that your net change in altitude is going to end up being equivalent, right? Even though they took a really roundabout path to get from point A to point B, it doesn't matter from a path integral perspective because their net change in altitude was the same as yours, even if their path was not very efficient. By the way, parameterizing this spiral to start at a prescribed starting point and ending point, that was a huge pain. But I did it, and I ran this through Mathematica. So I did the integral of field dot tangent for this x2 of t, y2 of t, where t goes from 0 to 25 pi over 4. And Mathematica spits out 0.597 again. Your net change in altitude is up about half a kilometer. Now again, was it a great idea to have Mathematica compute this path integral? Not necessarily, because we have a piece of given information in this problem that would probably make this calculation easier, but we're going to ignore that for a second. And again, our change in height from our starting point to our ending point, up about 0.5 kilometers. All right, so this is a general phenomenon that we can really observe for any gradient field. And that is, if we have the same starting point and the same ending point, our net change in altitude is going to be the same. Our path integral is going to be equal for C1 and for C2, as long as we have the same starting point and the same ending point and we have a gradient field. So this is called path independence for gradient fields. The net flow, this is a property that we can use when we're computing the net flow of a gradient field along an open curve. So if we have our vector field and it happens to be a gradient field, and C1 and C2 are different curves that share the same starting and ending point, then the path integral along C1 is equal to the path integral along C2. And this statement looks super fancy, right? That this looks like a difficult idea, but it really is pretty intuitive. It's just that our net change in altitude from our starting point to the ending point is the same when we have a surface associated with our vector field, when we have a gradient field. And so a gradient field, as long as we have no singularities, a gradient field with no singularities is said to be path independent. The net flow of a gradient field along any two curves connecting the same 2 points is the same. And you'll see this talked about in a physics class in relation to work. I've seen examples like this with if you're carrying a box from the first floor up to the 5th floor of a building, if you go straight from the 1st floor to the 5th floor, versus your friend maybe got confused and went all the way up to the 50th floor and then walked back down to the 5th floor. Well, the amount of work you did is the same if you both started at the 1st floor and you both ended at the 5th floor. It doesn't really matter what path you took to get there. The amount of work that you did was the same at the end of the day. So this is an idea that you'll see come up in a physics class as well. All right, so then what we really want to wonder now is we had a parabolic path. We had a crazy spiral that I'm not going to try to draw. And from a computational perspective, maybe neither of those were a really good choice of a path. Now that I know that I can pick any curve connecting my starting point to my ending point, you want to ask yourself, from a mathematical perspective, what is the simplest way to get from point A to point B, which of course is a straight line. So we can use path independence to come up with a replacement curve so that instead of having to integrate along a parabola, which can be quite difficult, or integrate along a spiral, which could be even more difficult, we could just replace both C1 and C2 with just a much better option, which would be parameterize a straight line connecting point A and point B. The most direct path between 2 points is going to be a straight line. And when I say the most direct path, I'm talking about from this 2-dimensional plot. What is my most direct path? If you look at the surface itself, you might argue that maybe there was a better path. But when we're talking about this gradient field living in 2-dimensional space, a straight line is the most direct path from point A to point B. So look what I did here. I know that I end my path at 0, -1. I know I start my journey at -2, 2. So here's my starting point. And then if I do q minus p here, then I get 2, -3 for my vector when I compute q minus p. This is my starting point p. This is my ending point q. And now that I have this parameterization, my bounds are nice because I know that this goes from t equals 0 to t equals 1. So my limits of integration look pretty nice. My curve looks pretty nice. And it all plugs into f of xy pretty well also. Now, here's the argument that someone could make that, like, well, was this really a better curve? Because look, from the perspective of a hiker, you have to walk down into this valley and back up again. But we're not talking about what would be the most pleasant for our hiker. We're talking about a path that would be the easiest to compute from a computational perspective. So our poor hiker has to go all the way down into the valley and back up again. But the mathematics that allows us to compute this is much easier if we take this straight line. And again, I ran it through Mathematica. I had the computer do the work, and unsurprisingly, about half a kilometer up. We gain about half a kilometer in altitude from our starting point to our ending point. But now is probably the right time to start to mention that all three of these calculations were not necessarily a good choice because of how much given information we had in this problem. Now, normally you wouldn't have the equation for the surface given to you, but by the fundamental theorem of calculus, I probably shouldn't have computed any path integrals for this example, because if I know the equation for the surface, I should just plug in the coordinates of my ending point minus the coordinates of my starting point, and that will also give me my net change in altitude. I'll show you that on a later slide, but kind of something to think about, that in this case, it was a little bit silly what I did. But most of the time, you're not going to know the equation for f of x, y, in which case you do have to use one of these path integrals. All right, so here it all is together. So by the way, picking this red curve is called finding a replacement curve. If you're lucky enough to have a gradient field, then you could pick a straight line going from your starting point to your ending point to replace whatever curve you had at the beginning of the problem. Anyway, let's look at the shortcut here. So again, we use the chain rule here. So gradient dot tangent becomes df dt. Then we use the fundamental theorem of calculus. The integral of the derivative is the function back again. So we just compute f of x of b y of b minus f of x of a y of a, or f at my ending point minus f at my starting point. What is my altitude at the end of my hike minus what was my altitude at the start of the hike? And you get that same answer of 0.597. So pretty cool. Lots of different ways to get the same answer to the same problem. All right, last thing that I should mention here is, let's just think strategy when you're studying for a quiz. What you want to look out for on any sort of quiz or midterm that you take on this material is you want to start all of your problems by checking, is my given vector field a gradient field? Because if it is a gradient field, we now know two really cool tricks. One trick is if you have a closed curve, the net flow of our gradient field along our closed curve is going to equal 0. Our net change in altitude is going to be 0. That could save you a ton of time on a quiz, because instead of crunching the numbers, just put down an answer of 0 and write a sentence explaining your reasoning, you're done. And then if you have an open curve, and they give you, let's say you have this crazy spiral shape on the quiz or midterm or whatever that you're taking. Well, if you try to compute the path integral along this spiral, you're never going to finish the quiz, because that integral is going to be very, very difficult to compute by hand. So the shortcut is check if your m comma n is a gradient field, and if it is, just find out what your starting point is, find the coordinates of your ending point, and then parameterize a line segment connecting those 2 points, and you can compute your path integral, the integral of field dot tangent, for your replacement curve, and you're going to have a much more computationally accessible problem. Guys, this is such an important idea, what we're discussing here, that it is called the fundamental theorem of line integrals. Also, it looks just like the fundamental theorem of calculus. So just apply the chain rule, then apply the fundamental theorem of calculus, and look at this. The integral of field dot tangent is f of x of b y of b minus f of x of a y of a. This idea is so foundational to vector calculus that it is the fundamental theorem of line integrals. The net flow of a gradient field along a curve is just your change in height, your change in f along your path. All right, so moving along, what I want to remind you guys is not every vector field in the universe is a gradient field. So there are some vector fields out there that are not gradient fields, in which case you can't really use a replacement curve. So when you start these problems, the first thing you want to do, you never assume that you have a gradient field. You want to take your vector field and check, do I have a gradient field? So you'd use the gradient test. You compute dm dy, which equals 1 in this case, dn dx, which equals 2 in this case. You do not have a gradient field. Therefore, we don't have path independence, and we are not guaranteed that the net flow of our vector field along a closed curve is going to equal 0. So you want to be very careful in these cases. So you actually have to crunch the numbers. So in this case, don't get fooled by a problem like this. We know this is not a gradient. So the flow along for C1 and the flow along for C2, we expect these path integrals to compute to different values. They could be the same value, but that would just be luck. It is much, much more likely that these two path integrals compute to completely different values. And so I'm going to run the numbers for C1. And you could follow these steps later. You can pause the video and go through these steps if you want some extra practice. But you get 11 halves for the net flow of our vector field along this curve C1. So the net flow of the vector field along this curve is, don't say clockwise or counterclockwise. It's in the direction of parameterization because we have an open curve. Clockwise and counterclockwise don't make sense. So it's just, basically it's just with or against the tangent vectors, right? With or against the direction of parameterization. In this case, with the direction of the tangent vectors. Now we can do the same computation for this parabola. And when you run the numbers, you get a different value, 41/6. Again, it's with, so the net flow of the vector field along this open curve is in the direction of parameterization with the direction of the tangent vectors, but the actual value is different. And we would expect that when we don't have a gradient field. So here they are side by side. This is just showing you that only gradient fields are path independent. You cannot apply that property to vector fields in general. You're going to get yourself into some trouble. And then finally, the last caveat I want to give you is all of these special properties of gradient fields depend on you having a gradient field that does not have any singularities in the way. So when you compute the gradient test, the other thing you want to check is, does your gradient field have any singularities? And if so, all of these cool properties like the path integral along a closed curve equals 0 or path independence, those depend upon having a gradient field that doesn't have singularities. So I think the shortcuts fall apart or potentially fall apart when you have singularities. Now we'll talk a lot more about singularities next chapter. Next chapter is all about dealing with singularities and what to do when you have a singularity and what shortcuts remain and what shortcuts no longer work. So don't worry, we'll go into a lot more detail after winter break. But for now, what I want to mention is when you compute the gradient test and you realize you have a gradient field, don't stop analyzing that vector field yet. Double check and see if there are any points where your vector field is undefined, and if so, your shortcuts are going to fall apart or potentially fall apart. If you want all of those freebie properties that you get with gradient fields, no singularities allowed. So here's an example. Here's what I'm trying to warn you about. So I think I was a little too wordy on the previous slide, but let me show you here. Basically, what can happen is you take your vector field, you compute the gradient test, and it looks like your vector field has passed the gradient test. And in a sense, it has, right? This means that we have a surface associated with this vector field. And it's a pretty cool looking surface, but there's an issue. We end up with a bunch of points in our vector fields that are undefined. Anytime x equals 0 or y equals 0, this vector field is undefined. And when that happens, when you try, basically the idea here is, let's say you have a closed curve and you're trying to compute the net flow of your gradient field along your closed curve. Well, everything on the x-axis is a singularity. Everything on the y-axis is a singularity. And so you have a curve that's encapsulating a bunch of singularities. It's hitting some singularities here, but everything on these green lines inside of this curve is a singularity. And that's going to throw off all of our logic. Because remember, everything was based on, thinking about going on a hike. And it was all very straightforward, right? Like we have a mountain, and we're just, going on a loop around the mountain, and our starting altitude is equal to our ending altitude. And so our net change in altitude is 0. Well, that's all going to fall apart if you have a weird surface that has a bunch of points that go to infinity or negative infinity or are otherwise not well behaved. So in this case, we don't get to say that the net flow of the gradient field along this closed curve is equal to 0 because of the presence of singularities. All right, guys, thank you so much for tuning in. I hope you enjoyed this video, and good luck on your triad problems.